let's recapitulate on what we saw in sections 10.3 and 10.4. In 10.3, I gave you a function f of x, I gave you a value called c, and we formed what we called the Taylor series of that function about x equal to c. And this is what it looked like. Within sigma notation, that. We're going to cut terms out. We would have f of c, f prime c, x minus c, f double prime c, 2 factorial, x minus c squared, on and on and on it goes. In order to show that that series converges to this function, we had to go through Taylor remainders. We had to show that for a certain interval of convergence that the Taylor remainders approach 0, then we could write this, that that series has this sum. That was 10.3. Gave you the function, gave you the c, expanded the function in a series, called the Taylor series. When c is 0, called the Maclaurin series. Along came 10.4, where the starting point was a power series. Wrote out a few terms, a0, a1x minus c, a sub 2, x minus c squared, and on and on. Objective, find out the values of x for which the series converge, called again its interval convergence, and then once you know the values of x for which the series converges, you ask, what is its sum? And if f of x is its sum, then we wrote this, right? But the difference, the starting point here, started with the function, started with the c, made the series. Here, gave you the series, asked, when does it add up, and what does it add up to? Turned 10.3 around. Question is, are power series Taylor series? We can certainly say that a Taylor series is a power series. This has the same form as that. Question is, are power series Taylor series? If the answer is yes, then we're really talking about the same thing in both those sections, simply coming from a different point of view. And the answer is, it is true that every Taylor series is a power series, and I intend to show today that every power series is a Taylor series of its sum. That this is the Taylor series of that. That's the objective today. And we're going to find out that that has immediate consequences that are extremely, extremely useful. Subject 10.5's heading is finding Taylor series for functions. And if I put in brackets, without going through remainders. I need a theorem to do that. Theorem. This theorem, not going to prove, would take me a week to prove it, and it would take me into the realm of what is called uniform convergence, and that is probably the most difficult topic I've ever had to teach in my life, and I don't think we need to do that. It says, suppose f of x equals summation n equals 0 to infinity a sub n x minus c to the n with radius of convergence, which is positive. So I'm telling you, I've got a power series, it's got an interval of convergence, this is its radius, and this is the sum of that series inside that interval of convergence associated with that r, or the open interval of convergence. Then the theorem says the following. If you wanted, or if you did the following, summation n equals 0 to infinity a sub n x minus c to the n. What have I done? I've taken this series and I've differentiated every term with respect to x. The derivative, bypass the constant, bring down the power n, lower the power by 1 to that. This is another new series. Question is, what do you think it adds up to? And I think, the hopeful thing would be that it adds up to f prime of x. And that is what this theorem says, that this series will add up to that series. Furthermore, if I did the following, summation n equals 0 to infinity, a sub n over n plus 1, x minus c to n plus 1. What did I do now? I took this series and I integrated it every term. I raised the power by 1 and I divided by the new power. Question is, does it have a sum? And what is it? And the answer is yes. It's the antiderivative of f of x. And we know that when we integrate, we should always know why. Constant integration. So this theorem says basically that you can differentiate and integrate power series term by term. You can't do that in general. If these were arbitrary functions in here, that is not always possible. It depends upon that concept I mentioned a minute ago about uniform convergence. But for power series, it says, yes, you can do it. And both series have the same radius of convergence. That one. That same radius of convergence. So both, if you integrate or differentiate a series term by term, you do not affect its radius of convergence. You can affect its interval of convergence. They both would have the same open interval of convergence, because if the r is the same, then the open interval of convergence does not change. What could change is the interval of convergence. The only difference between the endpoints, when you differentiate a series, term by term, if the interval of convergence did not include the endpoints, this won't either. If this one did contain the interval or the endpoints, this one might or it might not. You could, under differentiation, lose endpoints if they were there in the first place. When you integrate, if the endpoints were in, for the interval of convergence here, they would still be in. If they weren't here, they might be in here. So under integration, you might pick up endpoints. But remember, we're dominantly interested in open intervals of convergence. So to us, for most of the time, we wouldn't worry about whether you lost or you picked up endpoints. But you can. Pick them up or lose them, depending upon whether you integrated or differentiated. I can now use this theorem to, I want that. I want to now prove, we know that every power series in x minus c, or every Taylor series is a power series. What we're wanting to prove here is that every power series is the Taylor series of itself. So do you agree that what I have to prove is, I have to prove that these are equal to those. If I want to prove that this is the Taylor series of that, I have to prove that these are equal to those. That's what I would have to prove. Right? So let's state that as a theorem, and then let's try and prove it. Theorem. Every power series in X with r greater than 0 is the Taylor series of its sum. Proof. So let's take a power series, f of x, n equals 0 to infinity, a sub n, x minus c to the n. Written out, a0, a1, x minus c, A2 x minus c squared, and on and on. Now remember, what I have to prove, if I want to prove that this is the Taylor series of that, I have to prove, as we said a minute ago, that a sub n is equal to the nth derivative at c over n factorial. That's what I have to prove. All right? I have to prove that a0 is equal to when you plug in 0. I have to prove that a1 is what you get when you plug in here. So let's write that down. A0 has to be equal to f, 0 derivative c, 0 factorial. That means f at c. I have to prove that a sub 1 is the first derivative at c over 1 factorial. I have to prove that a sub 2 is the second derivative at c over 2 factorial, and so on. These are things that I have to prove then if I am to prove that this is the Taylor series of him. All right, let's go for this one. How do I prove that this is true? It will take you one line to prove it. Discover that line. Answer? Why don't I take this line and set x equal to c? If I do, I get f of c. What do I get on this side? You put x equal to c, that's gone. That's gone. They're all gone. All that's left is a0. That's what I wanted to prove. One down and infinity to go. All right, what next? Well, suppose I differentiate this. I can do that by this theorem over here, and I know it's the same radius of convergence. So let's do that. F prime of x is equal to, I can differentiate that. Let's just do it there. Differentiate that, gone. Differentiate this, a1. Differentiate that, 2, a2, x minus c. Differentiate the next one. It's got a q, 3. A3 x minus c squared, on and on and on. I want to prove this. What if I set x equal to c? What do I get? I get f prime c is equal to x equal to c, gone, gone, gone. All you're left with is a1. Is that what I wanted to prove? Answer yes. 1 factorial is 1. Let's do one more. If I differentiate it again, f double prime of x, I can do that. This is a series. I know it converges. Got a r greater than 0. I can differentiate this one. You do? Gone. Differentiate that. 2a2. Differentiate that. 3.2 a3 x minus c. Dot, dot, dot. Set x equal to c. What do I get? F double prime c is equal to 2a2. Is that this one? The answer is yes, it is. All right? You can see that if I differentiated it again for a triple prime, then I'm going to see in here a 3 factorial, and that's what the next one would be. Triple prime over 3 factorial. So carrying this procedure on, we get exactly what we want. Now, once you've got this power series that adds up to that, then this is the Taylor series of that function. So in other words, again, Taylor and power series are one and the same. Every Taylor series is a power series. Now, every power series is a Taylor series. Now, this is extremely beneficial. Consider the following. I give you a function. I want its Taylor series. So what do? I don't worry about the Taylor series. I say, if I could find a power series of the right form, then it has to be the Taylor series. So says that theorem. So if I want a Taylor series about 5, I go find a power series in x minus 5, knowing that if I get one, it has to be the Taylor series. So in other words, to find Taylor series and Maclaurin series, you forget that and you say, go find a power series of the right form, and it has to be the Taylor series or Maclaurin series. So I don't have to do remainders at all. Because I know when I find them, if I've done it legitimately, I'm working with power series, they've got an interval of convergence, and that's going to turn out to be the interval of convergence from the Taylor or the Maclaurin series. So a whole bunch of examples. There's various techniques that we can use, and technique 1 I call algebraic manipulations. For instance, find Maclaurin series for sine of 3x. Now, when I say find the Maclaurin series, you know that must also be assured that when I get it, that it's got an interval of convergence. So I look at this thing and I say to myself, hey, I happen to know the Maclaurin series for sine x. It was on the board the other day. Summation n equal minus 1 to infinity, or 1 to infinity of 2n plus 1 factorial, x to the 2n plus 1. And I know that that series converges for all x. Now this series says that you can put anything you want for that x as long as you put it there, the same thing. Or if you put something here, then you have to put the same something there. And it doesn't matter what that x is, so why don't we simply take all those x's and put in 3 x's instead? So writing then that the sine of 3x is summation n equals 0 to infinity minus 1 to the n, 2n plus 1 factorial, 3x to the 2n plus 1. That must be true. Because again, this x can be anything I want, provided x is between minus infinity and infinity. Well, it says anything. So this is going to be true for minus infinity less than 3x less than infinity. But that's the same thing as minus infinity less than x less than infinity. So there it is. I don't like that 3 in the bracket, so I would probably rewrite it as summation n equals 0 to infinity minus 1 to the n, 3 to the 2n plus 1, 2n plus 1 factorial, x to the 2n plus 1. I'm done. It took me all of 2 lines to do it. And that's what's going to go on in all of these examples in this section. We will take known series and we will get other series from them. And this first technique is using algebraic manipulations. And the series that I'm going to use are the ones that I had on the board the other day. Geometric, sine x series, cos x series, and e to the x series. Those 4. And there'll be one more in this section called binomial expansion later. Right? So I use these known series to find Taylor series and Maclaurin series for other functions. So there's our first straightforward example. Second example. Find Taylor series for e to the 2x plus 1 about, and if you were here, I'd like to pick the number. Pick anybody you want. Say about x equal 4. Suppose you want the Taylor series of that guy about x equal 4. What you think is what we said earlier. Don't think Taylor. You say to yourself, power. Now here is the greatest thing that I can tell you, and it's not in the book. In all of these examples, you should make what I call a box. And say to yourself, when I am done, I'm going to put in this box what powers I want to see. Since I want a Taylor series about x equal to 4, then when I'm done, I better see powers of x minus 4. Because that's what a Taylor series would have. Here, if I had put the box down, I would have put x. But when I said Maclaurin, you automatically know that is powers of x. But it doesn't hurt to write the box in every example, whether it says Maclaurin or Taylor. So what I say to myself is now, I need to produce a power series for this function in powers of x minus 4. If I get it, I know it's the Taylor series about x equal to 4. What I know is, I know the series for e to the x is Maclaurin series, x to the n over n factorial. Whatever x I put here, it's there. Whatever x you put here, it's there. And x can be anything. So I say to myself again, I need to see x minus 4s. So I'm going to get them. Nobody in their right mind would do what I'm going to do next unless they knew where they were going. I need to see x minus 4s. So I'm going to get them. Now that is not the same as this. If I expand that, that's 2x, but I also get minus 8. I don't want minus 8, I want 9. So how do I I want a 1, so how do I put a 9 there? Is that the same now? And the answer is yes. I could separate this into e to the 9 and e to the 2, x minus 4. What I can now do is say, hey, if you want this, why don't you take this, and every time you see an x in it, put in a 2, x minus 4. We would get then e to the 9 summation, n equals 0 to infinity. 2 x minus 4 to the n over n factorial. And what am I looking at? I'm looking at a series in powers of x minus 4, and I can say, that has to be my required series. I would just turn around to rewrite it as summation, n equals 0 to infinity. I'll take the e to the 9th in, because I don't like things up front. I'd have a 2 to the n. I would have an n factorial, and I would have an x minus 4 to the n. There it is. There is the Taylor series of this function about x equal 4. Valid for minus infinity less than 2, x minus 4 less than infinity, and that simplifies to that. And we're done. So all we did again was, same as the first one. The first one, we manipulated this one by replacing x by 3x. This one, we manipulated this guy, but we had to prepare the way to get the x minus 4s, and we did it. So there's 2 algebraic manipulations. Here's a third one.